have a roughness, big roughness, then the mobility is dropped down. And next. So this shows that I'm talking about the direct layer. So on top of that, the semiconductor layer is deposited. And in my case, I use a pentasand by vacuum deposition. So the interaction between pentasand and direct layer is important for the formation of pentasand layer. And actually the growth mechanism determine the morphology and also the ordering of the pentasand. So we're talking about the surface property of dielectric, such as surface energy and roughness. The bulk property also important, but which determine the carrier density, but today we're focusing on only surface property. So the two topics, one is surface energy, and secondly we talk about surface roughness. So surface roughness, surface energy actually, as I said, interaction between direct layer and semiconductor layer is important for the morphology and the packing of semiconductor material and crystallinity also. So this is literature survey showing that by increasing the surface energy, we have grain size is increasing and then decrease if you have a higher surface energy. This shows this is the mobility and this is the grain size. So if you increase the grain size and you have a larger mobility, the reason is if you have a large grain size, then you have a less amount of grain boundary. Grain boundary, you can have a loss of trap site exist. So if you have a large grain size, then you can expect a large mobility. So this is kind of very opposite result. In this case, showing that the mobility is, this one is a silicon dioxide substrate, direct layer. And right in this one is, this SiO2 was modified by the OTS, octadecyl trichlorosilane. Then we have a reduced surface energy. Then also we have a smaller grain size. In this case, even though we have smaller grain size, we have more compared with just SiO2. We have about 20 times and 10 times of mobility is obtained. So which is very opposite to the previous result and general concept of grain size. So in this study, we focusing on the effect of grain size and also by how we can, even though we have small size, how we can have improved mobility. And another topic is roughness. If you have a roughness, this roughness can be act as a trap site. So this trap site can inhibit the uniform and large grain, so grain size will be smaller, and also affect the nucleation density if you have a roughness like this. So again, this is also literature saying that by increasing the roughness from 1.7 angstrom to 92 angstrom, you see that grain size is decreasing a lot. And this figure, IV curve showing that the slope is actually the slope mobility. Mobility is dropped down by decreasing the grain size. It actually is a lap surface. Next. It's showing that if you have a very smooth surface, the charge carrier is moving very nicely. Suppose if you have a roughness like this carrier cannot go in, kind of going back. If you increase the temperature or imply the electric field, you can overcome this energy value. Next. So our objective of this talk is surface and roughness effect how affect the morphology of pentasand and the crystal structure, which is closely related to pentasand FET characteristics. So the effect of surface energy first. So we control the dielectric surface energy. Actually, we use the polyimide as a substrate, and in order to reduce the surface energy, we incorporate this polydimethyl siloxane in the backbone. So the amount of decrease of surface energy is determined by the amount of PDMS content and also the molecular weight of PDMS. Next. So this is showing the processing condition. Spin coated and pre-baked 80 degrees C, imidized 3 step at the end of 250 degrees C. Throughout the talk, the notation is like that. Homopolyimide, without siloxane, we have a highest surface energy. By incorporating 4,300 molecular weight of PDMS, 1%, we have less surface energy, and further decrease with 10,000 molecular weight, 20%. So, in this way, we measure the surface roughness through contact angle measurement. Homopolymer is like 50 and 40, and if you add 10,000 molecular weight, 30. Compared with pentasand is about 40. So homopolyimide is higher surface energy than pentasand. In the case of silicon modified one is less than pentasand. And this is roughness showing that almost same roughness. This is again showing the roughness of the polyimide surface by the AFM on about 3 angstrom. This shows the AMF image of thermally evaporate pentasand film on polyimide dielectrics with different surface energy with 44 nanometer thickness. By decreasing surface energy by incorporating PDMS, we decrease the surface energy, and also we decrease the grain size. So that's why we can investigate the grain size effect on mobility. This is XRD result, out of plane mode. Actually, the pentasand is aligned vertically to the dielectric layer surface. So the homopolyimide has a stronger peak, means the layer by layer structure is well pronounced compared with the silicon modified one. It's much smaller this. This is the design of my OFET device. So gate was used as a heavily doped silicon wafer. Dielectric layer was polyimide with 3 different kinds, and pentasand as an active layer, source and drain as gold. This is a typical transfer curve, IV curve, showing that the red color is the lowest surface energy one. So this showing that this is the homopolyimide. So the characteristic is much improved by reducing the surface energy of dielectric layer. The mobility is a slope of this, highest mobility obtained with the lowest surface energy. This showing again by decreasing the surface energy, we have a decreased size of grain, but we have improved mobility, from here to here. So about 0.2 to 0.4 in this case. Actually, this value is very dependent on the purity of the pentasand. Usually we obtain about more than one, but in this cases we have not the pure pentasand, so it's a little lower. Next. So we try to understand why we, even though in the literature says that the grain size is high, then we have a higher mobility, but we have opposite result. So we investigate that. As I said, actually the pentasand compared with the substrate, pentacene surface energy lower, then we have wetting of pentacene is very well. So if you have a homopolyimide, we can have a easily cover up the surface. Then we have a layer by layer structure like this. First layer, second layer. And in the case of silicon modified one, surface energy of pentacene is higher than substrate. So the pentacene cannot cover up whole surface. Then just we have droplet state, like form an island structure like this. So this shows the APM morphology, showing that most of the covered up with pentacene, and this white one is uncovered one. It's quite opposite. We have a thickness only 2.4 thickness. Actually, pentacene itself is like vertically lined up is 1.5 nanometer. So this showing that most of them are covered up with the pentacene, and some part is still bacon, but the thickness is only about 2.4 thick. For the case of low surface energy material, only 50% is covered up. So, and also, even though we have only 2.4 thickness of pentacene deposition, some island part has about 7 nanometers, or about 5 to 7 nanometer thickness. So this showing that only is a deposition of pentacene about 1.5. This is monolayer. It's about this, and this is bacon part. So the second layer and third layer and go on. Finally, we have a dendrite structure, dendrite morphology. So this is a typical. If you have a large surface energy, then pentacene we have 2D mode of growth. And in the case of low surface energy, then we have first layer with most of them bacon, and the nucleation is further in the bacon space, and then about 10 nanometer we have a kind of web connected structure, and for the cross packing about this thickness we have this kind of morphology. So this is a higher magnification of previous slide. About 10 nanometer we actually find out increase of mobility that are interconnected each other. For the deposition of pentacene, we have more cross packing. So we have more for the cooking, we have more cross packing. So we have a better mobility than the other two-dimensional growth mode. So summary, actually we vary the surface energy using polyimide gate direct layer by incorporating siloxane group. So by decreasing the surface energy, we have reduced grain size, but we have better mobility, more than 2 times or 3 times. And so next. The reason being is instead of 2D growth, we have 3D growth. Therefore, we have more tighter packing and interconnection between the pentacene grain. In fact, that if you have a 2D growth with a higher surface energy, then even though we have a very easily the first layer is formed, but the first layer is not connected. Some disconnected part is still exists. On top of that, the second layer and third layer is formed. Therefore, the 2D layer, even though it's easily wet, but some parts still disconnected compared with 3D growth. So this is the first part, and this goes to the next part. The surface roughness effect. This is surface roughness is reduced to 7 angstrom from 15 angstrom, and the grain size is much larger, bigger than before. So we studied the morphology of pentasene by XRD and NEXAF, and also studied the device characteristic. So we try to investigate effect of roughness. We made a device, silicon substrate coated with aluminum as a gate, and the aluminum was anodized to form alumina, aluminum oxide, act as a gate dielectric, and this has a very high surface energy. So in order to match with the pentasene, we reduce the surface energy by applying polymethyl methacrylate. So the surface energy from 170 to 45, and also to control the roughness of the surface, we vary the thickness of PMMA. Higher thickness of PMMA, we have a smaller roughness, and thin layer is about 15 angstrom roughness. So this shows that the smooth surface, 7 angstrom roughness. This is about 15 angstrom roughness. You can see some modulation. This is SCM cross-section of dual gated dielectrics, alumina and PMMA. Next. This is again showing that with only 4 nanometer thickness of pentasene, we have a large grain size with smaller roughness. We have a 32 nanometer thickness. We have a dendrite structure, but still larger than this rougher surface. And also we have agroplane mode of XRD. Then we see that the red one is a rough surface. So smoother surface, we have a well-aligned layer bio structure. So this is a more thicker one, also same thing. So in other words, if you have a roughness is smaller, then we have a well-aligned layer by layer structure. But this is a, okay, next, previous one. Previous one. Okay. This is outer plane mode, but the electron moving this way, so outer plane is not related with the direction of mobility. So next one. So we studied in-plane mode. In-plane mode is the direction to the crystal has a lot of different directions. So it is an in-plane mode of XRD data, showing that with this 8 nanometer thickness, we have 3 peaks. We have 16 nanometer, we have about 5, and that 5 different peaks. So each peak actually relates with the crystal plane direction. So closest plane has the fastest charge direction, carrier direction. So the first peak is the closest part, which is diagonal direction. This the way of the hole is moving. The second and third direction is third peak is this horizontal direction. This herringbone structure. So this one and this is 2 and third one, and fourth and fifth one is this vertical direction. Much longer spacing. Next. This is again confirming that this pentasene is lined up vertically to the direct layer surface. So X-ray is coming this way like 90 degree, and this way is 220 degree of incident angle. When you see that the pi transition is 90 degrees higher, this one is the sigma direction, this vertical direction is 20 degrees higher. For the case of larger roughness, also the same data. So that means X-ray is this way, then electric field is like this, and the pi coupling is this way, is parallel each other. So we have a higher intensity at the 90 degrees C. When you vary the roughness or have some kind of difference, which is rougher surface, we have a smaller intensity means which coincide with outer plane XRD mode. Next, this is design our device, substrate gate, and the Dielectrics active layer. In order to only find out the effect of roughness, we have to control the capacitance, because if you vary the capacitance, then we have a different amount of charge carrier that affect the mobility. So we get rid of this capacitance effect. To fix the capacitance, we vary both PMMA and anodized layer thickness. So in this way, we can find out the same capacitance. So we only study the effect of roughness. Next. So this is the way we developed the anodized aluminum oxide in the potential step. By applying voltage like 1 volt, we obtain 1 nanometer aluminum oxide. So we control the thickness. And actually, this is a very rough surface of alumina. This rough surface can be reduced by applying polymetal methacrylate on top of that. So this is the result showing this nicely obtained IV curve, and also we measure the mobility and also threshold voltage through this curve with roughness about 15 angstrom roughness, with mobility is 1.28 centimeter square volt second. On-off ratio is 10 to 6. Threshold voltage minus 10 volt. Sub-threshold swing is 1.5 volt. And capacitance is about 11 nanofarad. Next. The smaller roughness, 8 angstrom. Mobility is a little bit higher, but the other property is almost same. Next. A little bit reduced. The 7 angstrom case is mobility is 0.31, and 10 to 6 is about the same as before. So basically the roughness versus mobility is almost same for the less than 1.5, 15 angstrom thickness, roughness. So a little bit change, but not much change between these ranges. So IV result, we have the same capacitance, almost same capacitance, and mobility is about 0.28 to 0.31, and on-off ratio same, substrate swing almost similar, and substrate voltage is almost 10 to 11. So summary, we control the surface roughness with the dual direct layer, PMMA and anodized aluminum oxide. So within 15 angstrom roughness from XRD data showing that there is not much difference, particularly the in-plane mode. So that means the IV curve mobility also similar. So 15 angstrom is not we don't have to worry about the roughness. Maybe we have to worry about if you more than 15 angstrom, but in this case, within the 15 angstrom roughness, we have a well-ordered cofacial pentasystem structures. Thank you.